This paper presents an analysis of conversational AI multi-agent interoperability frameworks and introduces the novel architecture proposed by the Open Voice Interoperability Initiative, also known as OVON, Open Voice Network. The authors aim to enhance the capabilities and scalability of AI interactions across various platforms by establishing universal APIs based on natural language, enabling interoperable interactions among diverse conversational AI agents, including chatbots, voicebots, videobots, and human agents. The proposed framework is designed to generalize, being replicable and accessible via open repositories, with the main purpose of significantly enhancing the capabilities and scalability of AI interactions. A new discovery specification framework is introduced, designed to efficiently look up agents providing specific services and to obtain accurate information about these services through a standard manifest publication, accessible via an extended set of natural language-based APIs. The authors highlight the growing importance of chatbots and voicebots, citing a chatbot directory website that reports over 183,000 bots related to Facebook Messenger and Amazon Alexa skills alone. According to an analysis by Tidio.com, roughly 1.5 billion people are using chatbots, and this number is expected to continue growing, with chatbots projected to become the primary customer service interface by 2027. The proposed architecture is designed to address the limitations of current conversational AI systems, which often lack interoperability and scalability. By establishing a standardized framework for multimodal AI agency communications, the authors aim to enable seamless interactions among diverse agents and to facilitate the development of more sophisticated and effective conversational AI systems. The paper is structured to provide a comprehensive overview of the proposed architecture, including its main components and key benefits, as well as use cases for deploying standard multimodal AI agency communications. The authors also discuss the significance of their contribution and its potential impact on the field of conversational AI. The author's approach is based on the concept of agentic AI, which emphasizes the importance of agency and autonomy in AI systems. By establishing a standardized framework for multimodal AI agency communications, the authors aim to enable more sophisticated and effective conversational AI systems that can interact seamlessly with humans and other agents. The paper assumes that the proposed architecture will be widely adopted and that it will have a significant impact on the field of conversational AI. However, the authors also acknowledge that there are limitations to their approach and that further research is needed to fully realize the potential of their proposed architecture. Future work will focus on further developing and refining the proposed architecture, as well as exploring its applications in various domains, including customer service, healthcare, and education. Conversational AI interoperability is a crucial aspect of creating seamless user experiences, but current approaches have limitations. The independent modality components approach uses a standard API for collaboration, offering modularity but limited independence among assistants. Agentic hardwired collaboration involves hardwiring assistants together, allowing for flexible addition of new functionalities but requiring familiarity with all APIs and common technology. The inter-agent communication language approach focuses on requests and task performance, reducing dependency on internal structures but requiring detailed knowledge of secondary agent capabilities and interpretation of fine-grained semantics. In contrast, the Open Voice Conversation Envelope API introduces a novel approach, enabling multiple independent assistants to collaborate seamlessly with minimal requirements on cooperating assistants. This approach supports various technologies and channels, including voice, video, and text, and simplifies the addition of new assistants, reducing complexity. The Open Voice Conversation Envelope API allows assistants to pass user requests to secondary assistants, which interpret natural language, making it an attractive solution for conversational AI interoperability. Table 1 provides a detailed comparison of the different approaches, highlighting their benefits and drawbacks. The Open Voice specifications impose very few requirements on cooperating assistants, making it an attractive solution for conversational AI interoperability. The Open Voice Interoperability Initiative has released the first version of the Interoperable Conversation Envelope specification, with further updates available. This work builds upon previous research, such as the DARPA Communicator Program, which supported collaboration among multiple dialogue managers but coordinated communication through a central hub. The key features of the Open Voice Conversation Envelope API include its ability to support different technologies and channels, minimal requirements for integration, and simplified addition of new assistants. However, its reliance on natural language interpretation may impact accuracy. Overall, this approach offers a novel solution for conversational AI interoperability, enabling independent assistants to collaborate seamlessly and efficiently. Conversational AI agents are poised to become ubiquitous, leading to a proliferation of specialized agents that will need to collaborate to achieve tasks. To facilitate this collaboration, the Interoperable Conversation Envelope specification has been developed, enabling agents with varying levels of intelligence and specialty to communicate with each other using unstructured natural language. The Open Voice Interoperability framework defines a set of event types that can be sent between agents, including utterance, whisper, invite, buy, request, publish manifest, and find, propose assistant. These events support simple text and can be extended to support audio and other media in the future. The framework draws no distinction between human agents and automated agents, recognizing that language-capable AIs will interact with each other in a similar way to humans. A state diagram representation is used to model the behavior of AI agents, illustrating the different states an agent can occupy and the transitions between these states based on specific events or conditions. The key components of the state diagram include states, representing the different conditions or modes the conversational AI agent can be in during a conversation, and transitions, representing the changes from one state to another triggered by specific user inputs, agent messages, or internal events. The framework enables agents to initiate requests or respond to requests, and chains and trees of agent interactions are possible and encouraged. Agents can be in a wide variety of internal states that are not of concern for interoperability among agents, and the state diagrams shown only describe states relevant to interagent collaboration. The Interoperable Conversation Envelope specification provides a practical solution for facilitating interoperability between language-capable AIs with varying levels of intelligence and specialty. The use of state diagrams to model the behavior of AI agents provides a useful tool for understanding and designing the interactions between agents. The framework assumes that conversational AI will reach human-level intelligence in the long term, enabling interoperability between agents to use the same mechanisms as humans, such as email, instant messaging, and phone calls. By providing a foundation for the development of conversational AI agents that can interact with each other and with humans in a seamless and natural way, the Interoperable Conversation Envelope specification enables more effective collaboration and task achievement. Conversational AI relies on the interactions between serving and demanding agents, facilitated by standardized frameworks like the Interoperable Conversation Envelope diagrams. A serving agent provides services, information, or assistance to users or other agents, responding to requests, performing tasks, and delivering outputs based on its capabilities and inputs. In contrast, a demanding agent initiates requests or tasks, seeking services, information, or assistance from other agents or systems. Notably, an agent can assume either role at different times. The Open Voice Network, OVON, conversation envelope is a universal JSON structure that enables human or automatic agents to participate in conversations interoperably. Figure 1 illustrates the states and transitions of a serving agent that successfully provides a response to an utterance or whisper conversation envelope, progressing from the idle state to the ready state upon receiving an invite standard message envelope event. Listing 2 provides an example of a post request sent to an AI agent specializing in book and author information, demonstrating the JSON structure of the conversation envelope. Figures 2 and 3 represent the serving agent's states and transitions when it fails to provide a response and combines both use cases, respectively. Figure 4 highlights the states and transitions related to a demanding agent, illustrating its progression from the idle state to the ready state and subsequent interactions. The interoperable conversation envelope diagrams facilitate seamless interactions between serving and demanding agents, enabling them to engage in conversations that fulfill the needs of users or systems. These diagrams provide a foundation for understanding the complex dynamics of conversational AI, highlighting the importance of standardized structures and protocols in facilitating effective communication between agents. The underlying mathematical concepts are rooted in finite-state machines and probabilistic models, which enable agents to navigate through various states and transitions based on the inputs they receive. The use of JSON structures and standardized message envelope events ensures interoperability and facilitates the development of conversational AI systems that can engage with diverse agents and systems. This work contributes to the development of standardized frameworks for conversational AI, enabling the creation of more sophisticated and effective AI systems that can interact with humans and other agents in a seamless and efficient manner. Future work may focus on extending these frameworks to accommodate more complex conversational scenarios and integrating them with other AI technologies to create more comprehensive and intelligent systems. In conversational settings, serving and demanding agents exhibit distinct states and events that significantly impact interaction dynamics. Figure 2 illustrates the states and events for a serving agent when it fails to find a response, while Figure 3 provides a comprehensive overview of all states and events related to a serving agent. In contrast, Figure 4 outlines the states and transitions for a demanding agent, highlighting its ability to transition from the consuming response state back to the ready state upon sending an utterance or whisper event. This transition occurs when the demanding agent actively engages in the conversation by providing input. The demanding agent's state transitions also reveal that, upon conversation termination, it returns to the idle state, as indicated by the by-standard envelope event. These state diagrams and event transitions underscore the complex interactions between serving and demanding agents, emphasizing the importance of understanding their behaviors to optimize conversation efficiency and effectiveness. The paper's focus on detailed state diagrams and event transitions demonstrates a thorough exploration of agent interaction models, aiming to provide insights into optimizing agent communication strategies. By examining the intricate relationships between serving and demanding agents, this research contributes to the development of more sophisticated artificial intelligence systems capable of navigating complex conversations efficiently. The findings highlight the need for a deeper understanding of agent behaviors to improve overall conversation dynamics, ultimately enhancing the performance of AI systems in conversational settings. In multi-agent systems, the efficient allocation of tasks among agents is crucial for optimal performance. To achieve this, assistant manifest specifications enable agents to describe their capabilities, facilitating a discovery process for finding agents with specific skills. This process is demonstrated through two state diagrams. The first diagram illustrates the states and transitions involved in a demanding agent searching for the manifest details of a target agent. The process begins in the capability search state, where the demanding agent requests the target agent's manifest details. Upon receiving the request, the target agent transitions to the waiting for manifest state, where it prepares to publish its manifest. Once published, the demanding agent transitions to the ready state, where it can utilize the target agent's capabilities. The second diagram shows the states and transitions involved in a demanding agent searching for assistance available to perform specific tasks. The process begins in the assistant search state, where the demanding agent broadcasts a request for assistance with the required capabilities. The available assistants respond with a list of their capabilities, causing the demanding agent to transition to the waiting for assistant list state. Once the list is received, the demanding agent transitions to the ready state, where it can allocate tasks to the suitable assistants. These processes utilize standard message envelope events, including request manifest, publish manifest, find assistant, and propose manifest. By leveraging assistant manifest specifications, agents can efficiently discover and allocate tasks to agents with specific capabilities, enhancing overall system performance and efficiency. The Smart Errands use case demonstrates the interaction of multiple agents to coordinate and optimize a series of errands, adhering to the Universal Open API specifications for Agentic natural language multimodal communications. Emmett, a human, seeks assistance from Cassandra, his general AI assistant, to manage and streamline his errands efficiently. The scenario involves multiple AI assistants at various service points, including Pat at Bloomingtown Florist, Andrew at the post office, Charles at the hardware store, and Sukanya the host at Thai Palace. Emmett's goals are to order flowers for his wife's birthday, check on the repair of a chainsaw at the hardware store, order carry-out Thai food for lunch, and find the cost of mailing a 2-pound package to California. The AI large language model (LLM) technologies employed in this scenario include Cassandra, based on GPT 3.5 Turbo, Pat using Llama 2, Andrew using a rule-based application without LLM, Charles using Claude.ai 3.5 Sonnet, and Sukanya using GPT 4.0. The conversation begins with Emmett interacting with Cassandra, who connects him with the local florist shop. Pat, the AI assistant at the florist, engages with Emmett to discuss flower selection, ultimately resulting in an order for red proteas with eucalyptus in a clear vase. This conversation demonstrates the ability of multiple agents to interact and coordinate to achieve Emmett's goals, highlighting the potential of agentic natural language multimodal communications to facilitate efficient and streamlined interactions between humans and AI assistants in various scenarios. This use case showcases the coordination of multiple AI assistants, each with distinct language models and capabilities, to achieve a common goal. The Universal Open API specifications provide a framework for seamless communication and coordination between these agents, enabling efficient and effective interactions. The Smart Errands use case illustrates the potential of agentic natural language multimodal communications to transform the way humans interact with AI assistants, enhancing productivity and efficiency in various domains. In a scenario presented by the authors, a multi-agent dialogue system showcases the capabilities of an advanced conversational AI. The scenario begins with Emmett placing an order for a bouquet of red proteas with eucalyptus in a clear vase through flower shop agent Pat. Pat confirms the order and thanks Emmett for his purchase. Next, Emmett asks Central AI agent Cassandra to check the status of his chainsaw repair at the local hardware store. Cassandra invites hardware store agent Charles to join the conversation, and Charles informs Emmett that his chainsaw will be ready by tomorrow afternoon. Following this, Emmett places a carry-out order from his favorite Thai restaurant through Sukanya, the restaurant manager. Sukanya offers him the special of the day, pad Thai with shrimp, and Emmett agrees to add 2 spring rolls as an appetizer. He chooses to pick up the order in an hour. The scenario also includes a conversation between Emmett and Andrew, the postmaster, regarding the cost of mailing a 2LB package to California. Andrew explains that the cost depends on the shipping service chosen, with priority mail starting at around $8.70. Throughout the scenario, Cassandra serves as the central hub, connecting Emmett with various agents to fulfill his requests. This demonstrates the AI's ability to manage multiple conversations, understand context, and provide relevant information to users. The authors highlight the potential applications of such a system in various domains, including customer service, e-commerce, and logistics. The OVON sequence diagram illustrates the conversation envelope messages exchanged between human and AI agents in a multi-agent system, showcasing seamless integration of technology across different AI models and frameworks. In the first use case, human Emmett interacts with his general AI assistant Cassandra, and other AI assistants, demonstrating independence from underlying large language models and AI technologies. The second use case, the Smart Library experiment, involves human Lee, who requires assistance with literature research. Multiple AI assistants, characterized by distinct roles and technologies, collaborate to provide support, including Yuri, Andres, and Kaya, powered by GPT 3.5 Turbo, Mistral 7B Instruct v0.3, and Hugging Face 4, Zephyr 7B Beta, respectively. The conversation begins with Lee's request for information about books written by Lydia Koidula, prompting Yuri to request a list of assistants with relevant knowledge from Andres. Andres provides a list of assistants, including Kaya, Heli, and Kalev, along with their URLs, and Yuri requests Kaya's manifest. The OVON framework facilitates collaboration between AI assistants with diverse capabilities and technologies, enabling a seamless conversation flow. The sequence diagram and conversation transcript highlight the system's potential to support complex tasks and provide personalized support to users, illustrating the OVON conversation envelope messages exchanged between agents. Key aspects of the OVON framework include the use of conversation envelopes, which enable the exchange of messages between human and AI agents, and the independence of the framework from underlying AI technologies. The Smart Library experiment demonstrates the potential of the OVON framework to support complex tasks, such as literature research, and provide personalized support to users. The use of distinct roles and technologies for each AI assistant highlights the flexibility and scalability of the framework. The OVON sequence diagram and conversation transcript provide a detailed illustration of the conversation flow, showcasing the potential of the framework to support seamless collaboration between AI assistants. The OVON framework has the potential to support a wide range of applications, including personalized assistance, education, and research. The use of conversation envelopes enables the creation of complex conversation flows, supporting the integration of multiple AI assistants with diverse capabilities and technologies. The independence of the framework from underlying AI technologies ensures that the system can be adapted to various use cases and applications. Future work includes exploring the potential of the OVON framework in real-world applications and further developing the system to support more complex tasks and conversations. In a demonstration of coordinated, specialized support, an AI agent named Yuri interacts with other agents to provide information about Estonian books and authors. When asked about books written by Lydia Koidula, Yuri engages with Andres to identify an assistant with better expertise. Andres suggests Kaya, among others, and Yuri retrieves the necessary information from Kaya, which is then relayed back to the user, Lee. This scenario showcases the AI framework's ability to provide integrated support, independent of specific large language models and conversational AI technologies. The sequence diagram in Figure 8, Appendix C, illustrates the exchange of main OVON conversation envelope messages between the agents involved. This exchange highlights the AI system's ability to integrate various technologies to meet specific user needs, demonstrating a versatile and adaptable AI system. Future enhancements for the interoperability specifications are proposed, including the representation of multimodal interchanges among agents, support for multi-party conversations, and formats to enable agents to exchange background information, conversation history, and other context. Additionally, the redaction of sensitive data is suggested. These enhancements are expected to extend the applicability of the specifications to a broader range of use cases, further demonstrating the AI system's potential for coordinated, specialized support. A novel approach is proposed to enhance conversational AI security, ethics, and accountability within the Open Voice Network (OVON) specifications. This involves developing a universal set of open APIs for agentic natural language multimodal communications, leveraging the Open Voice Conversation Envelope API. Key benefits of this approach include loose coupling of assistants, flexibility, and ease of integration, as well as technology agnosticism and support for multiple communication channels. The proposed architecture for interoperable conversational AI assistants is designed to be replicable and accessible via open repositories, including the OVON specifications and the Sandbox, an experimental browser assistant system that implements interop dialog event specs and supports OVON envelopes. Future directions for enhancements are outlined to address the complexities of conversational AI security, ethics, and accountability, building on the work of the Open Voice Trustmark initiative. These enhancements include an enhanced authentication, authorization, and accounting (AAA) framework, bias mitigation mechanisms, transparency guidelines, ethical interaction protocols, accountability tracking, and sensitive data redaction and encryption. These advancements will strengthen the framework's capability to handle security risks, ensure ethical interactions, and maintain clear accountability. By enabling independent conversational assistants to collaborate, this approach offers significant advancements in enhancing the capabilities of conversational AI platforms in managing security, ethical interactions, and accountability. This research paper explores the development of interoperable standards for voice-activated systems, a crucial step towards seamless integration of various voice platforms. The authors acknowledge the invaluable contributions of the Open Voice Interoperability team, specifically John Stein, Jim Larson, and David Atwater, in shaping these standards. Additionally, the Bureaucrat team is recognized for their expertise and resources. The paper delves into the complexities of voice interoperability, highlighting the need for standardized protocols to facilitate communication between different voice-activated systems. The authors introduce the concept of a voice ecosystem, comprising various devices, platforms, and services that must interact seamlessly to provide a cohesive user experience. A key aspect of the research is the development of a novel framework for voice interoperability, which enables the integration of multiple voice platforms through a standardized interface. This framework is built on a modular architecture, allowing for the incorporation of various voice recognition engines, natural language processing algorithms, and device-specific protocols. The authors present a detailed analysis of the technical requirements for voice interoperability, including the need for standardized APIs, data formats, and communication protocols. They also discuss the importance of security and privacy in voice-activated systems, highlighting the need for robust authentication and authorization mechanisms. The paper includes a comprehensive evaluation of the proposed framework, using a combination of simulations and real-world experiments to assess its performance and scalability. The results demonstrate the effectiveness of the framework in enabling seamless voice interoperability across different platforms and devices. The authors conclude by highlighting the significance of their research in enabling the widespread adoption of voice-activated systems, and outline future work directions, including the development of more advanced voice recognition algorithms and the exploration of new applications for voice interoperability. The Interoperable Conversation Envelope Specification establishes a standardized framework for conversational AI systems, facilitating seamless communication across diverse platforms and devices. Central to this framework are a set of defined events that enable interoperability. The utterance event represents a user's spoken or text-based input, serving as the fundamental unit of conversation. Conversely, the by event signals the termination of a conversation, providing a clear endpoint for interactions. The request manifest event and publish manifest event play critical roles in facilitating the exchange of metadata between conversational AI systems. These events enable systems to negotiate capabilities and preferences, ensuring that interactions are tailored to the specific requirements of each platform or device. This negotiation process is crucial for achieving seamless communication and effective information exchange. The standardized events defined by the Interoperable Conversation Envelope Specification provide a foundation for developing conversational AI systems that can interact with one another in a meaningful way. By establishing a common language for conversational events, this specification enables the creation of more sophisticated and interconnected conversational AI systems. This, in turn, has significant implications for the development of more effective and user-friendly conversational interfaces. Key to the success of this approach is the ability of conversational AI systems to accurately interpret and respond to standardized events. This requires a deep understanding of the underlying events and their roles in facilitating communication. By providing a standardized framework for conversational events, the Interoperable Conversation Envelope Specification helps to ensure that conversational AI systems can communicate effectively, regardless of the platform or device on which they are deployed. The Interoperable Conversation Envelope Specification has significant implications for the development of conversational AI systems, enabling the creation of more sophisticated and interconnected systems. By providing a standardized framework for conversational events, this specification helps to ensure that conversational AI systems can communicate effectively, driving innovation and advancement in the field. The conversation envelope object structure is a crucial component of the proposed framework, defined as a JSON object comprising several key elements. The OVON field contains metadata about the conversation, including the schema version and URL. The conversation field specifies the conversation ID, while the sender field provides information about the sender, such as the from and reply to URLs. The events field is an array of events, each represented as a JSON object with three key value pairs: to, event type, and parameters. The to field specifies the intended recipient, the event type field defines the type of event, and the parameters field is an object containing event-specific parameters. The parameters object is a collection of key value pairs, where each key corresponds to a parameter name, and the value is an object containing the parameter values. An example of a conversation envelope JSON post request is provided, illustrating the structure of the object when sending utterance and whisper events to a smart library AI assistant specialized in author and book information. This example demonstrates the practical application of the conversation envelope object structure in representing complex conversations between multiple entities. The structure enables efficient and organized communication between various components, facilitating the exchange of information and enabling advanced conversational AI capabilities. The provided page presents a JS-own formatted HTTPS post request using the OVON universal APIs, specifically designed for conversational AI applications. This request comprises several key components, including the reply to URL, response code, and a list of events. The events list contains three distinct event types: invite, utterance, and whisper. The invite event includes a parameters object with a to field, specifying the URL of the intended recipient. This event type is likely used to initiate a conversation or invite a user to engage with the conversational AI system. The utterance event represents a spoken or text-based input from a user, with a parameters object containing a dialogue event field. This field includes the speaker's ID, a timestamp for the event, and a features object with a text field. The text field contains the actual user input. The whisper event is similar to the utterance event, but with a different event type. It also includes a parameters object with a dialogue event field, containing the speaker's ID, timestamp, and a features object with a text field. The text field in this case contains the user's follow-up question. The use of these event types and the structure of the request suggest that the OVON universal APIs are designed to handle complex conversational flows, including multi-turn dialogues and contextual understanding. The inclusion of speaker IDs and timestamps also implies that the system is capable of tracking user interactions and maintaining context across multiple events. The page does not provide explicit information on the limitations or assumptions of the OVON universal APIs, but it is likely that the system relies on natural language processing (NLP) and machine learning algorithms to interpret and respond to user input. Future work may involve expanding the API's capabilities to handle more complex conversational scenarios or integrating with other AI systems. The JSON post response example presented illustrates the structure and elements of a conversation envelope, version 0.9.2, as defined by the Open Voice Network schema. This conversation, with ID conva_1,699,812,834,794, originates from the Smart Library APIs and indicates a successful operation with a status of 200, described as OK. The events array contains an utterance event with parameters that include a dialogue event attributed to the speaker ID, assistant. This event spans a time period starting at 20,240,713 t 19 hours 18 minutes and 25 seconds. 855z. The features of this event include text with a MIME type of text, plain, and tokens representing the spoken words. The text within the tokens is a summary of Harry Potter and the Philosopher's Stone, the first novel in the Harry Potter series written by J.K. Rowling. It mentions the publication dates and the change in title for the United States edition, Harry Potter and the Sorcerer's Stone. This JSON post response example demonstrates how the Smart Library AI agent processes and responds to user queries, providing relevant information based on the context of the conversation. This exchange highlights the agent's ability to understand and generate human-like responses, utilizing its knowledge base and natural language processing capabilities. The assistant manifest object structure for a smart library system serves as a prime example of how conversational AI agents are designed to function effectively. This structure comprises two essential sections: identification and capabilities. The identification section includes key details such as the service endpoint, organization, conversational name, service name, role, and a synopsis of the AI agent's purpose. In this case, the agent specializes in providing information about books and authors. The Capabilities section outlines the keywords, languages, descriptive texts, modalities, and content type that the AI agent can handle. For instance, it can understand keywords like books, authors, ISBN, and editors, in English, ENIS. The agent is designed to provide information about authors and books, with a content type of application, JSON. This manifest structure is crucial for the discovery and integration of the smart library system with other conversational AI agents or applications. It ensures that the system can be easily identified and its capabilities understood by potential users or developers looking to integrate it into their own projects. This example highlights the importance of structured data and clear definitions in building conversational AI systems that can effectively communicate and exchange information with humans and other machines. Listing 5 presents a conversation envelope JSON post request designed for interaction with a smart library AI assistant, specializing in author and book information. The request is sent by an external entity to the smart library URL, adhering to a schema version of 0.9.2 to ensure a standardized format for communication. A unique conversation ID is generated and specified within the conversation object, while the sender is identified as an external bot located at the provided URL. The events object contains an array of event-related data, with a request manifest event specified as the event type. This signifies that the external entity is soliciting the smart library for information, specifically requesting its manifest, which serves as a catalog or directory of its capabilities, resources, or services. The smart library is expected to respond with its manifest, enabling the external entity to explore and potentially leverage the library's capabilities. The schema version, conversation ID, sender ID, and event type are essential components of the request, facilitating the smart library's processing and response generation. The standardized structure of the conversation envelope ensures seamless communication and information exchange between parties, integrating the smart library's specialized knowledge with external applications or services. The use of the request manifest event type exemplifies the flexibility and extensibility of the conversation envelope framework, allowing diverse use cases and applications to be built upon this foundational structure. The JSON response to a request manifest in the OVON Universal API comprises multiple components, including schema version, conversation ID, sender details, and events. The publish manifest event is of primary interest, carrying parameters such as manifest identification, capabilities, and descriptive texts. The manifest identification section contains essential details, including service endpoint, organization, conversational name, service name, role, and synopsis. In this example, the service endpoint is empty, the organization is your_organization, and the conversational name is Smart Library. The service name is Books and Authors AI Agent, with a role as a book specialist, and a synopsis describing it as an AI agent specializing in providing information about books and authors. The Capabilities section lists relevant keywords, including books, authors, ISBN, and editors, and supports languages such as ENIS. The descriptive texts are authors and books information. The modalities are text, and the content type is application, JSON. Sender details indicate that the request is sent from, to. This JSON response is critical for understanding how the OVON Universal API handles requests and responses, particularly in the context of a smart library application. In the interoperable AI assistant scenario, a sequence diagram illustrates the interaction between various components in the context of errands, as depicted in Figure 7 of Appendix C. The sequence initiates with the user sending a request to the AI assistant to perform an errand, such as booking a flight or making a restaurant reservation. The AI assistant, acting as a mediator, forwards this request to the errand service, which is responsible for processing and executing the task. The errand service then interacts with the task management system to retrieve relevant information, such as the user's preferences and profile data. This information is utilized to execute the task, and the errand service updates the task management system with the task status. Subsequently, the errand service notifies the AI assistant of the task's completion, and the AI assistant, in turn, informs the user of the outcome. This sequence diagram highlights the seamless interaction between the AI assistant, errands service, and task management system, enabling the efficient execution of errands while ensuring user preferences are respected. The diagram showcases the AI assistant's role as a mediator, facilitating communication between the user and the errands service, and demonstrates the potential of interoperable AI systems in streamlining complex tasks. The interoperable smart library AI assistant scenario, as depicted on page 22 of the research paper, presents a comprehensive vision for enhancing citizen engagement and access to information. This vision is visually represented through a sequence diagram, accessible via the provided repository link, which illustrates the interactions between various entities in the smart library system. The sequence diagram showcases how different components of the smart library communicate with each other to provide seamless services to users. This includes interactions between the AI assistant, user devices, and library databases, demonstrating the system's ability to facilitate information retrieval, book lending, and other library services efficiently. The use of sequence diagrams in this context serves as a valuable tool for understanding the complex interactions within the smart library system. This enables developers and researchers to identify potential bottlenecks, optimize system performance, and ensure smooth user experiences. Moreover, this scenario highlights the potential of AI-driven technologies in enhancing public services, such as libraries, by making them more accessible, efficient, and user-friendly. By leveraging advanced technologies like AI and IoT, these systems can be designed to offer personalized services, automate routine tasks, and provide real-time information to users. In conclusion, the interoperable smart library AI assistant scenario underscores the importance of interdisciplinary research in developing innovative solutions that can transform public services and improve citizen engagement.